There is a reason your Azure OpenAI bill keeps climbing, even though usage looks flat. 3 hidden taxes are embedded in every agent call. The context tax inflates prompts with irrelevant documents. The reasoning tax sends simple questions to the most expensive model. And the autonomous tax burns credits while nobody is watching. Here's how to find them. The promise versus the invoice. Microsoft sold you AI as part of your Microsoft 365 subscription. Copilot sits in Teams, Outlook, and Word. It feels included, but that inclusion has a hard boundary. The moment you build a custom agent in Copilot Studio, attach a knowledge source from SharePoint, or call an Azure OpenAI model through a Power Automate flow, you have left the license and entered consumption billing. And consumption billing does not care about your seat count. Most finance teams discover this when the first Azure invoice arrives. They see a line item for Azure OpenAI and assume it is a trial or a mistake. It is not. The M365 Copilot license covers classic answers and generative responses for licensed users, but custom agents, external-facing bots, and autonomous actions run on separate meters. Those meters bill in tokens, not seats, and tokens are priced per million, with input and output charged separately. Here is where the math gets painful. Azure OpenAI token prices match the direct OpenAI API, but your total Azure cost runs 15 to 40% higher once you add support plans, networking, data egress, storage for logs and vectors, and the observability stack. A prompt that costs $1 in raw tokens can easily cost $1.40 in reality. That overhead is not a rounding error. At scale, it is the difference between a pilot and a budget crisis. The billing layers stack like this. At the top, you have Microsoft 365 Copilot licenses. For internal users, these absorb many Copilot Studio interactions without extra credits. Below that, Copilot Studio uses Copilot credits for agent actions, generative answers, and graph grounding. Each credit is roughly 1 cent on pay-as-you-go, or 0.8 of a cent if you buy capacity packs. Below that again, any custom Azure OpenAI deployment bills per million tokens with separate rates for input and output. And underneath everything, Azure infrastructure charges for compute, bandwidth, logging, and security. Most organizations never mapped these layers before they started building. They assumed the license covered the stack. In reality, the license covers the top floor, and every floor below it has its own meter. If you are running a customer-facing agent that queries SharePoint, calls GPT-5 for summarization, and logs every interaction to application insights, you are paying across all 4 layers. The agent is not expensive because your users are greedy. It is expensive because the architecture was never designed for cost visibility. This is the first structural flaw. You cannot control what you cannot see. And most Microsoft environments were built for productivity, not for token accounting. The tools were designed to make AI easy to deploy. Nobody told finance that easy deployment comes with invisible consumption until the invoice shows up. That is why the starting point is not a cost-cutting exercise. It is an audit. Before you optimize a single prompt, you need to know which layer is bleeding and how much. Because the fixes we will build later only work if you apply them at the right layer. A cache saves Azure OpenAI tokens, but it does not save Copilot credits. A cheaper model saves token cost, but it does not fix retrieval bloat. You need the map before you need the medicine. The context tax. The context tax is the biggest hidden cost in most Microsoft AI deployments. It hits when your retrieval pipeline pulls too many documents and stuffs them into the prompt without filtering. In a typical Copilot Studio RAG setup, the agent queries a SharePoint library or an Azure AI search index, gets back a set of chunks, and appends them to the user question before sending everything to the LLM. Most teams never question how many chunks or how large they are. Let me show you the math. Suppose your retrieval step returns 50 chunks, each averaging 500 tokens. That is 25,000 input tokens before the user question is even added. If the user asks a 10-word question, that adds maybe 20 tokens. So you are sending a 25,020 token prompt to answer a 10-word question. At GPT-5 global input rates, that prompt costs you over $30 per call in context alone. But the real damage is not the per call cost. It is the compounding. If that agent handles 1,000 queries per day, you are burning $30,000 per day on retrieval context. Over a month, that is $600,000 in input tokens. And most of those chunks were never relevant to the question. They were retrieved by a loose semantic search and included because the pipeline was built for recall, not precision. The problem is not RAG itself. RAG is the right pattern. The problem is lazy RAG. Lazy RAG retrieves broadly, does not re-rank aggressively, and concatenates everything into the prompt because it feels safer. The assumption is that more context reduces hallucinations. In reality, more context increases cost, slows response time, and often confuses the model with contradictory information from unrelated documents. Microsoft Copilot Studio and Azure AI Search give you the tools to fix this, but most implementations skip the tuning. They use default chunk sizes. They do not enable hybrid search with semantic ranking. They do not set top K limits. They do not filter by metadata. So the retrieval layer returns noise, and the LLM pays for every token of that noise. The fix is engineered retrieval, not more retrieval. You need to retrieve fewer, better chunks. That means smaller chunk sizes aligned with document structure, hybrid search combining vector similarity with keyword filtering, and metadata filters that restrict the search scope before the LLM ever sees a token. Top K should be 3 to 7 chunks, not 50, and every chunk should be scored for relevance before it enters the prompt. There is also a deeper layer. Even with good retrieval, the prompt itself often contains redundant system instructions, repeated formatting rules, and bloated conversation history. Every token in the system prompt is sent on every call. If your system prompt is 500 tokens and you send 10,000 calls per day, that is 5 million tokens of overhead. At GPT-5 rates, that is over $6 per day in instructions alone. Over a year, that is $2,000 for text the model already knows. This is the context tax. It is not a model problem. It is a pipeline problem. And it is the first place you should look when your bill is higher than your usage suggests. The reasoning tax. The reasoning tax is what you pay when you send every question to the most capable, most expensive model. Most teams default to GPT-5 Global or GPT-4o because they want the best possible answer. That is understandable, but it is not architecture. It is convenience. And convenience at scale is the fastest way to double a token bill. Look at the 2026 Azure OpenAI pricing. GPT-5 Global charges $1.25 per million input tokens and $10 per million output tokens. GPT-5 Mini charges 25 cents per million input and $2 per million output. GPT-5 Nano charges 5 cents per million input and 40 cents per million output. The gap between Nano and Global is 25 times on input and 25 times on output. If you are using Global to classify an email or answer a FAQ, you are paying 25 times more than necessary. The mistake is not using a powerful model. The mistake is using one model for everything. In a well-architected system, the task should choose the model, not the other way around. Simple classification, sentiment analysis, entity extraction, and FAQ matching do not need frontier reasoning. They need fast, cheap inference. Complex multi-step reasoning, legal analysis, creative drafting, and cross-document synthesis need the flagship. Most agent workloads are 80% simple and 20% complex. If you route everything to global, you are paying the flagship rate for the entire workload. This is where model routing changes the economics. Azure AI Foundry now offers a model router that is itself a trained language model. It sits between your application and the underlying LLM pool. Your code calls a single endpoint. The router reads the prompt, estimates the complexity, and sends the request to the cheapest model that can handle it. Simple questions go to Nano or Mini. Hard questions go to Global or GPT-5 Pro. You do not hardcode model selection. The architecture does it for you. The documented savings from intelligent routing sit around 60% for mixed workloads. That is not a minor optimization. That is the difference between a pilot that gets funded and a pilot that gets cancelled. And the router is deployed like any other model in Azure AI Foundry. You browse the model catalog, deploy the router, and call it through the same Azure OpenAI SDK you already use. The integration cost is low because the API surface does not change. Of course, there are constraints. You cannot force the router to use a specific model via API parameters. You cannot add your own fine-tuned models or external APIs to the pool. And the routing decision is opaque on a per-request basis. If your compliance team requires deterministic model choice for audit reasons, you should deploy specific models directly rather than routing through the abstraction. But for most internal and customer-facing agents, the trade-off favors the savings. The other half of the reasoning tax is output length. Output tokens cost roughly 8 times input tokens for GPT-5 Global. That means a verbose response is far more expensive than a long prompt. If your agent generates a 500 token answer when 100 tokens would suffice, you have just quadrupled the most expensive part of the bill. Setting max tokens limits, constraining response formats, and training the model to be concise are not quality compromises. They are cost controls, and at scale, they matter more than almost any other single setting. The autonomous tax and the 2026 cliff. The autonomous tax is the cost of agents that run without human throttle. In Copilot Studio, an autonomous agent can trigger actions, query knowledge sources, and initiate Power Automate flows based on events rather than direct user requests. That sounds powerful because it is, but every trigger consumes Copilot credits, and credits consumed while your team is asleep still show up on the invoice. The variability is the problem. A quiet month might use a few thousand credits. A busy month, where an agent triggers on every new SharePoint file or every incoming email, might use 100 times more. That burst pattern makes budgeting nearly impossible. Finance teams plan for steady spend. Autonomous agents deliver spikes. And because Copilot Studio builds credits per action, not per user session, the spike can happen without any increase in human users. This gets worse on November 1st, 2026. That is the date Microsoft removes seeded AI Builder credits from all tenants. If your organization is currently using Power Apps Premium or Dynamics 365 licenses, those licenses include a monthly pool of seeded AI Builder credits. Those credits have been covering many Copilot Studio and AI Builder experiments at low or zero marginal cost. After November 1st, they vanish. There is no automatic conversion. Your agents do not switch to a free tier. They start billing immediately. If you have not bought Copilot Studio capacity packs or set up pay-as-you-go billing in Azure, your agents will simply stop working. Or worse, if you have set up PAYG but not capped it, they will keep running and billing without limit. Capacity packs cost $200 per month and provide 25,000 credits. That works out to 0.8 of a cent per credit. Pay-as-you-go charges a full cent per credit. An agent that uses 10 credits per interaction will cost 8 to 10 cents per conversation. At 10,000 conversations per month, that is $800 to $1,000. At 100,000 conversations, it is $8,000 to $10,000 per month. And that is before you add Azure OpenAI token costs for any custom model calls. The same agent design can cost $8 per month or $800 per month, depending on how many actions it triggers, how many knowledge sources it queries, and whether it uses graph grounding. Graph grounding alone consumes roughly 10 credits per query. If your agent grounds every answer in Microsoft 365 data, you have just added 10 cents to every response before the LLM token meter even starts spinning. This is why the 2026 cliff is not just a licensing change, it is an architectural reckoning. Every agent built during the seeded credit period was built without cost pressure. Citizen developers could experiment freely. That freedom produced valuable prototypes, but it also produced inefficient architectures. After November, those inefficiencies become real money. And the organizations that survive the transition are the ones that audit their agents before the deadline, not after the invoice arrives. The Azure Cost Management Deep Dive. You cannot fix what you cannot measure. And in Microsoft AI environments, most organizations cannot measure. They see a single Azure OpenAI line item on a consolidated invoice and treat it as a black box. The first step in breaking that box open is Azure Cost Management, and the most underused feature inside it is natural language querying through Azure Copilot. Most finance teams export cost data into spreadsheets and build pivot tables. That works for static reporting, but it is too slow for operational decision-making. Azure Copilot lets you ask questions directly against your cost data. You can say, summarize my Azure OpenAI cost for the last 90 days broken down by model deployment. You can ask, what are the top 3 services driving my AI spend in East US? You can even run scenarios. How much would my cost change if GPT-5 usage increased 20% next quarter? The power of these prompts depends on your tagging discipline. If your resource groups are named RGProd001 and your deployments carry no metadata, the Copilot cannot segment your spend. It will return aggregate numbers that tell you nothing about which agent, which team, or which workload is responsible. Before you ask a single cost question, you need clean tags. At minimum, every Azure OpenAI resource should carry tags for environment, department, agent name, and cost class. Every Copilot Studio environment should map to a billing scope in the Power Platform Admin Center. Once your tags are clean, build a query rhythm. Weekly, ask for a trend summary by tagged agent. Monthly, ask for a breakdown by model, SKU, and region. Quarterly, run a what-if analysis against projected usage growth. The goal is not a report. The goal is a feedback loop where every spike triggers a question within 48 hours, not 48 days. There is also a second layer most teams miss. Azure Monitor Diagnostic Logs. Every Azure OpenAI deployment emits logs for every request, including input token count, output token count, model name, and latency. You can stream these logs to a log analytics workspace and query them with KQL. A simple KQL query can show you which agent consumes the most tokens per call, which hour of the day drives peak usage, and which user segments generate the longest prompts. This is not billing data, it is operational telemetry, and it is far more actionable than an invoice line item. The audit phase should produce 3 artifacts. First, a cost baseline. Total AI spend by layer by week for the last 90 days. Second, a token flow map, average input tokens, average output tokens, and peak concurrency for each agent. Third, an anomaly log. Any week where spend jumped more than 20% above trend with a hypothesis for why. If you cannot produce these 3 artifacts, you are not auditing. You are guessing. And guessing is how the context tax and the reasoning tax hide in plain sight. The Copilot Studio Consumption Estimator. Azure Cost Management covers the infrastructure layer, but Copilot Studio has its own meter, and that meter is not measured in tokens. It is measured in Copilot credits. Understanding the credit model is essential because the same agent can cost $8 per month or $800 per month, depending entirely on design choices. Microsoft provides an agent consumption estimator tool specifically for this purpose. You input your expected session volume, the number of generative answers per session, the frequency of graph grounding calls, and any Power Automate actions triggered by the agent. The estimator then projects your monthly credit consumption and compares prepaid capacity packs against pay-as-you-go billing. This comparison is not trivial. Capacity packs pool across the tenant and expire monthly, so over-provisioning wastes money. PAYG scales without limit but costs 25% more per credit. The wrong choice can add hundreds of dollars per month in either unused packs or premium PAYG rates. Credit consumption varies dramatically by agent behavior. A classic scripted FAQ answer consumes roughly 1 credit per response. A generative answer from a knowledge source consumes roughly 2 credits. Graph grounding, which queries Microsoft 365 data through the Microsoft Graph, consumes roughly 10 credits per query. Agent reasoning chains and autonomous actions can multiply the base cost by a factor of 10 or more. If your agent triggers a Power Automate flow with 100 actions, that adds roughly 13 credits. A single user conversation that touches all of these layers can easily consume 50 to 100 credits. At 1 cent per credit on PAYG, a 100 credit conversation costs $1. At 0.8 of a cent per credit via capacity packs, it costs 80 cents. Multiply that by 10,000 conversations per month, and the difference between good design and bad design is $2,000 per month. Multiply by 100,000 conversations, and it is $20,000 per month. The unit economics are not abstract. They are the difference between a sustainable agent and a budget review. The estimator also helps you size capacity packs correctly. If your projected monthly need is 90,000 credits, you need 4 capacity packs, providing 100,000 credits. That leaves a 10,000 credit buffer for spikes. If you buy only 3 packs, you cover 75,000 credits and the remaining 15,000 bill at the higher PAYG rate. The optimization is not about eliminating buffer. It is about sizing buffer accurately so you do not pay premium rates for predictable demand or waste money on unused capacity. Mapping your token flows. Cost control without architecture visibility is guesswork. A token flow map traces every request from the user through the agent, through retrieval, through the LLM, and back to the response. It exposes exactly where tokens are born and where they die. And it reveals which layer of your pipeline is the most expensive. Start with the user interaction layer. Check how many turns a typical session lasts and how much chat history is retained and resent with every new question. A 10-turn conversation, where each prior turn is included in the context window, can multiply token consumption by a factor of 5 or more. If you are not compressing or summarizing conversation history, you are paying for the same text on every turn. Next is the retrieval layer. Check how many chunks your RAG pipeline returns, what the chunk size is, and whether hybrid search is enabled. Most Copilot Studio agents use default settings here, and the defaults are not cost-optimized. Default chunk sizes in SharePoint indexing are often larger than necessary for question answering. Default top K values in Azure AI search are often higher than needed. And hybrid search, which combines vector similarity with keyword filtering, is frequently disabled because it requires extra configuration. Without hybrid search, your vector query returns broadly related chunks that share semantic neighbors but not topical relevance. Those chunks inflate the prompt and degrade answer quality at the same time. The prompt layer is where the hidden overhead lives. System prompts, formatting instructions, safety meta prompts, and grounding metadata are all prepended to every call. If your system prompt is 400 tokens and you send 5,000 calls per day, you are sending 2 million tokens of instructions daily. At GPT-5 global rates, that is $2.50 per day in system prompt overhead alone. Over a year, that is over $900 for text that never changes. Caching the system prompt or moving static instructions into the model deployment configuration can eliminate most of this. Finally, the model layer. Check which SKU is handling the request, what the max token setting is, and whether output length is capped or allowed to drift. Output tokens dominate cost for GPT-5 because output is 8 times more expensive than input. A model setting that allows 500 token responses when 100 would suffice is not a quality setting. It is a 5-fold cost multiplier on your most expensive meter. Build this map for each agent. Use KQL queries against Azure OpenAI diagnostic logs to extract real numbers. Use the Copilot Studio Analytics dashboard for credit data. And use Azure API management trace logs if you have a gateway in front of your endpoints. The map does not need to be beautiful. It needs to be true. And once it is true, you will almost always find that one layer accounts for 70% of your waste. Building your baseline and cost classes. Once your token flow map is complete, you need a baseline. A baseline is a snapshot of current cost per interaction, tokens per interaction, and peak latency for each agent. It is not a guess. It is a measured starting point against which every future optimization is judged. Without it, you cannot prove that a change saved money. You can only hope. Store your baseline metrics in an Azure Monitor workbook. Track weekly averages and monthly P95 peaks. Watch for drift. If your tokens per interaction creep up over time, that usually means your retrieval pipeline is degrading or your conversation history is growing unchecked. If your cost per interaction spikes on specific days, that usually means a new feature or a marketing campaign drove unusual traffic to an unoptimized path. With the baseline in place, introduce cost classes. This is the framework that prevents waste before it happens. Every agent workload gets classified into one of 3 tiers before deployment. Gold is customer-facing, SLA-backed, and complex. It gets the best model, the highest latency budget, and the most rigorous retrieval. Silver is internal tools and moderate complexity. It gets a mid-tier model, cached responses where possible, and standard retrieval. Bronze is FAQ, classification, extraction, and experimentation. It gets the cheapest model, aggressive caching, strict max tokens limits, and minimal retrieval. The classification happens before the agent is built, not after the invoice arrives. Platform teams publish the criteria. App teams justify any gold classification with an SLA and a business case. Silver is the default. Bronze is the sandbox, and no team can override the model assignment or cache policy without a platform review. This sounds bureaucratic, but it is the only way to prevent 10 teams from independently choosing GPT-5 Global because it feels safer. Safety is not a model choice. Safety is a pipeline choice, and cost classes make that explicit. The baseline and the classification framework together give you something most organizations lack, a shared language for AI cost. Finance can ask why an agent is gold. Engineering can show that gold status reduced escalation rates by 40%. Platform teams can monitor whether silver agents are creeping toward gold behavior, and everyone can see the same dashboard. That visibility is the foundation for everything that comes next. The architecture pivot. At this point, most cost guides tell you to monitor and hope. They give you dashboards, alerts, and reports. Then they recommend that you review your spending monthly and optimize where you can. That is not architecture, that is accounting. And accounting will not save you when your autonomous agents hit the Copilot credit meter at midnight on a weekend. The shift you need to make is from reactive cost cutting to structural cost prevention. You do not want to spend less on the same pipeline. You want to design a pipeline where the expensive path is never taken unless it is genuinely required. Every token should be justified before it is sent. Every model call should pass through a filter that asks whether a cheaper path exists. And every response should be cached so the next identical question costs nothing. There are 4 engineering levers that make this possible. They are not isolated tips. They are a system, and when you deploy them together, they compound, but when you deploy them alone, they underperform. The first lever is semantic caching. If a user asks the same question twice, or a question that is semantically equivalent, the system should reuse the previous answer. It should not regenerate. This eliminates redundant LLM calls at the gateway layer before the token meter ever spins. The second lever is prompt compression. Most enterprise prompts are bloated with retrieved documents, conversation history, and system instructions that are longer than necessary. Compressing the prompt before it reaches the LLM reduces input tokens without changing the answer quality. At scale, this cuts cost by a factor of 2 to 5. The third lever is model routing. Not every question needs a flagship model. A cheap model can handle FAQ, classification, and simple extraction. An expensive model should only see the tasks that genuinely need reasoning, synthesis, or creativity. Routing the task to the cheapest adequate model is the single biggest per-request cost win available in 2026. The fourth lever is capacity planning. Once your per-request cost is optimized, you need to buy capacity correctly. Pay-as-you-go is the right model for variable, experimental workloads. Provisioned throughput units are the right model for steady, high-volume production. Buying the wrong capacity commitment turns your optimized per-token cost into a stranded investment. These 4 levers work in sequence. Caching catches repeats before they reach the model. Compression shrinks what remains. Routing sends the shrunken prompt to the cheapest capable model. And capacity planning ensures you are buying that model's output at the right rate. Together, they form a cost architecture. And that is what we will build now. Semantic caching via Azure API management. Organizations regenerate the same answers thousands of times per day. A policy question about vacation days, a troubleshooting step for a common error, and a status update on a recurring process are not novel reasoning tasks. They are lookups disguised as conversations, and every time an LLM regenerates the answer, you pay for tokens that were already computed yesterday. Semantic caching solves this at the gateway layer. Instead of matching identical text strings, it embeds the incoming prompt into a vector and checks whether a semantically similar prompt was answered recently. If the similarity score is high enough, it returns the cached response with no LLM call, 0 tokens consumed, and millisecond latency. Azure API management implements this through 2 policies. On the inbound side, you add an Azure OpenAI semantic cache lookup policy. This policy sends the prompt to an Azure OpenAI embeddings deployment, converts it to a vector, and queries an external cache. On the outbound side, you add an Azure OpenAI semantic cache store policy. This policy embeds the prompt, stores the vector as a cache key, and stores the LLM response as the value with a configurable time to live. The external cache is typically Azure Cache for Redis with the Ready Search module enabled. Redis handles the vector similarity search at high speed. The similarity threshold is the tuning parameter that determines whether a cached answer is returned. A threshold of 0.92 to 0.96 is typical in production. Below that, you risk false positives where a vaguely related question gets an incorrect cached answer. Above that, you may miss valid cache hits because the threshold is too strict. The deployment steps are straightforward. First, deploy an embeddings model such as text embedding ADA002 in Azure OpenAI. Second, provision an Azure cache for Redis instance with ready search enabled. Third, configure an APIM backend pointing to the embeddings endpoint. Fourth, add the semantic cache lookup policy to your inbound processing and the semantic cache store policy to your outbound processing. Fifth, test with two similar prompts and confirm that the second one hits the cache. The validation is critical. Use the APM test tab and trace logs to verify that the first call reaches the LLM and stores the response, while the second similar call short-circuits and returns from cache. If you do not validate this, you may think you have caching when you actually have a broken policy that silently falls through to the LLM on every call. There are risks. Stale cache is the obvious one. If your policy answer changes because of a new regulation, the cached response may be wrong for hours or days until the time to live expires. Mitigate this with shorter TTLs for dynamic content and explicit cache invalidation hooks when source documents change. Privacy is another concern. Cached prompts may contain sensitive user data. Use per-tenant cache partitions, encrypt data at rest, and consider redacting personally identifiable information before embedding. False positives are the most subtle risk. If your threshold is too loose, a user asking about health insurance might get a cached answer about dental coverage because the vectors are close. This is not just a cost problem, it is a quality problem. The fix is conservative thresholds, human evaluation of cache hit quality during rollout, and continuous monitoring of user satisfaction scores after deployment. When semantic caching works, the impact is immediate. Cache hits return in milliseconds instead of hundreds of milliseconds or seconds. They consume 0 LLM tokens. And they reduce concurrency pressure on your Azure OpenAI deployment, which lowers the risk of throttling during peak hours. For high-volume agents with repetitive question patterns, cache hit rates of 40 to 60% are common. That is not a marginal saving. That is a structural change in your cost curve. Prompt compression with LLM Lingua. Caching eliminates redundant work, but most of your agent calls are not redundant. They are unique questions that require a live LLM response. The question is whether those unique questions need the full prompt you are sending. In a typical enterprise RAG pipeline, the prompt contains the user question, a system instruction, and a block of retrieved documents. That block is often 20,000 tokens or more, and much of it is noise. Redundant sentences, irrelevant paragraphs, formatting overhead, and metadata that the model does not need to answer the specific question. You are paying for every one of those tokens, and you are paying 8 times more for the output tokens that the model generates in response to all that noise. LLM Lingua is a prompt compression framework from Microsoft Research. It uses a lightweight encoder model to score every token or sentence in the retrieved context for relevance to the task. It keeps the important parts and discards the rest. Compression ratios of 2 to 10 times are typical, with some configurations reaching 20 times on long, redundant corpora. The quality loss is minimal because the compression is task-aware. It does not blindly truncate. It preserves the sentences that carry the signal. In Azure, LLM Lingua 2 models are available in the Azure AI Model Catalog. You can deploy them into an Azure AI Studio project and use them as a pre-processing step in prompt flow. The architecture is simple. Retrieval returns a set of documents. The LLM Lingua node compresses them to a token budget you specify. The compressed context is then passed to the main LLM along with the user query. The main LLM sees less text, generates faster, and costs fewer tokens, but it still receives the information it needs. There are 3 integration patterns. The first is prompt flow pre-processing. You insert an LLM Lingua node between your retrieval step and your LLM step. This is the easiest pattern if you are already using Azure AI Studio and prompt flow for orchestration. The second is backend integration. Your application calls a deployed LLM Lingua endpoint before calling Azure OpenAI. This pattern works for custom applications, Azure functions, and containerized services. The third is batch pre-compression. You compress your knowledge-based documents offline before embedding and indexing them. This reduces both storage and retrieval overhead, though it requires reprocessing when documents change. The tuning process matters. Start with conservative compression, targeting a 20 to 40% reduction in prompt length. Run an evaluation using Azure AI Studio's built-in evaluations feature. Compare answer accuracy, completeness, and user satisfaction between the compressed and uncompressed paths. If quality holds, increase compression. If quality drops, back off. Different tasks tolerate different levels of compression. Classification and FAQ can handle aggressive compression. Legal and medical compliance answers need conservative compression. Do not use a single ratio for all agents. Safety is also a consideration. LLM Lingua compresses content, but it does not validate it. If your retrieved documents contain sensitive data, compression does not remove it. And compression should never be your primary security control. Run Azure AI Content Safety on the final prompt and output. Apply the same RBAC, private networking, and encryption standards to the LLM Lingua deployment that you apply to your main LLM. The compressed pipeline is only as secure as its weakest node. For Copilot Studio environments, LLM Lingua is not a native feature. You cannot simply toggle it on. Instead, you need to build a custom RAG orchestrator using an Azure function or a custom API. Copilot Studio calls the orchestrator instead of using its built-in knowledge source. The orchestrator retrieves documents from Azure AI Search, runs LLM Lingua compression, calls Azure OpenAI, and returns the answer. This requires more engineering than a native Copilot Studio agent, but for high-volume scenarios, the token savings justify the build. The combined impact of compression and caching is where the architecture starts to pay off. Caching handles the repeats. Compression shrinks the unique requests. Together, they can reduce your input token volume by 50 to 70% before the model ever sees the prompt. And because output cost is driven by input complexity, shorter prompts often produce shorter, more focused answers. The savings cascade through both sides of the token equation. Model routing with Azure AI Foundry. Hard-coding GPT-5 global for every query is the fastest way to overpay. Most teams do it because it feels safer. They do not want to explain to a user why a cheap model gave a bad answer, so they send everything to the flagship and absorb the cost. At low volume, that cost is invisible, but at high volume, it is catastrophic. So the alternative is model routing. Azure AI Foundry now provides a model router that acts as a trained meta model between your application and the underlying LLM pool. Your code calls one endpoint. The router reads the prompt, estimates the complexity, and sends the request to the cheapest model that can handle it. Simple classification tasks go to GPT-5 Nano. Standard Q&A and summarization go to GPT-5 Mini. Complex reasoning, multi-document synthesis, and creative drafting go to GPT-5 Global or GPT-5 Pro. You do not hard-code these choices because the architecture makes them for you. The deployment is straightforward. In your Azure AI Foundry project, browse the model catalog and search for Model Router. Deploy it like any other model, giving it a name such as Model Router Prod. You receive an endpoint URL, an API key, and a compatible API version. Your application then calls this endpoint using the standard Azure OpenAI SDK, passing the router deployment name as the model parameter. The payload looks identical to a normal chat completion request. The router handles the selection internally. The savings are substantial. For workloads that are 80% simple and 20% complex, intelligent routing can reduce average model cost by roughly 60%. That is not a minor optimization. It is the difference between a pilot that scales and a pilot that gets shut down by finance. And the integration cost is minimal because you are already using the Azure OpenAI SDK. You change the deployment name and you are done. There are important constraints. The router pool is managed by Microsoft. You cannot add your own fine-tuned models to it. You cannot add external APIs or self-hosted open-source models. And you cannot force a specific model choice via API parameters. If your compliance or safety team requires deterministic model selection for audit reasons, the router is not the right tool. You should deploy specific models directly and build your own routing logic. Also, the routing decision is opaque on a per-request basis. You cannot look at a single response and know which model generated it. You can only see aggregate metrics. That means your monitoring strategy must focus on overall cost per request, average latency, and downstream quality scores rather than per-call attribution. If you need per-call model logs for regulatory purposes, you will need custom orchestration instead. For most business agents, these constraints are acceptable. The router is ideal for general-purpose copilots, developer productivity tools, and multi-tenant SaaS products where query complexity varies widely. It is less ideal for regulated environments that require fixed model versions or for use cases where a specific model has been certified for a specific task. The monitoring strategy matters. Because you cannot see individual routing decisions, you should define aggregate KPIs before deployment. Target a cost per request below a specific threshold. Target a latency P95 below a specific ceiling. Target a user satisfaction or escalation rate that matches or beats your current direct model baseline. If any of these KPIs degrades after routing, you can tune the prompt, adjust the generation parameters, or fall back to direct model deployment for that workload. Routing also pairs naturally with the other levers. A cached response never reaches the router, so cache hit rate directly reduces routing volume. A compressed prompt is what the router evaluates, so shorter prompts may be classified as simpler and routed to cheaper models more often. And capacity planning, which we will cover next, determines how you pay for the model the router ultimately selects. PTU versus PAYG, the capacity decision. Model routing optimizes per request cost. But how you buy capacity determines your total spend regardless of per request efficiency. This is the strategic decision that separates experimental workloads from production commitments. And most organizations get it wrong because they focus on sticker price rather than utilization math. Azure OpenAI offers two billing models: pay-as-you-go charges per million tokens with no commitment. Provisioned throughput units reserve a fixed amount of capacity and charge per PTU hour with monthly or yearly discounts. The advertised savings for PTU can reach 70% compared to PAYG list prices, but those savings only materialize at very high utilization. For GPT-5 Global in 2026, a yearly PTU reservation breaks even against PAYG at roughly 86% sustained utilization. That means you need to keep the reserved capacity busy at 86% or higher, 24 hours a day, 7 days a week. If your average utilization is 70%, PAYG is cheaper. If your traffic is spiky, with peaks at noon and troughs at midnight, sustaining 86% average is nearly impossible. Hourly PTU never wins on cost. It is useful only for short-term benchmarking or load testing. Monthly PTU rarely wins because the break-even point is near 100% utilization, which is practically unattainable in real workloads with any seasonality or downtime. Only yearly PTU can beat PAYG, and only for stable, high-volume, always-on production workloads. The practical framework is simple. Start every new workload on PAYG. Collect 30 to 90 days of real token throughput data. Compute your peak, average, and off-peak utilization. Then model the PTU cost at your actual utilization, not at ideal utilization. If your sustained average is above 85% and your workload is mission-critical with strict latency requirements, consider yearly PTU. Otherwise, stay on PAYG. There is a nuance that many calculators miss. Azure OpenAI introduced prompt prefix caching for PAYG workloads. If your prompts share a common prefix, such as a system instruction or a structured template, repeated calls are billed at a much lower cached rate. With cache hit rates above 50%, PAYG becomes even more attractive, and the PTU break-even threshold moves even higher. If you have built caching and compression correctly, your PAYG bill may already be lower than a PTU reservation would deliver. Some teams adopt a hybrid approach. They reserve a yearly PTU for their baseline load, the steady traffic they know will always be there. Then they use PAYG for bursts above the baseline. This improves average utilization of the PTU and avoids over-provisioning, but it adds operational complexity. You need 2 deployments, 2 monitoring dashboards, and logic to route traffic between them. Only do this if your baseline is large enough to justify the overhead. The hidden costs around PTU also matter. Support plans, networking, data egress, and logging scale with your overall Azure footprint. PTU deployments tend to be permanent and always on, which increases the share of these fixed overheads. PAYG lets you shut down environments faster when demand drops, which can shrink the surrounding infrastructure bill. The token price is only part of the equation. Fiscal guardrails and budget alerts. Engineers optimize for speed and quality. They do not optimize for cost unless cost is enforced. That is why the fourth layer of this architecture is not a technical lever, it is a governance lever. You need automated guardrails that make the cheapest path the default path and that alert you when someone overrides it. Start with Azure cost management budgets. Set a monthly budget for your total AI spend across Azure OpenAI, Copilot Studio, and related infrastructure. Configure 3 alert thresholds. At 50% of budget, send a warning email to the platform team. At 80%, trigger a logic app that posts to your operations channel and tags the workload owner. At 100%, block new deployments or throttle non-gold workloads until the next budget cycle. Do not rely on humans to notice a dashboard. Automated alerts are the only guardrail that scales. In Copilot Studio, set per agent credit caps in the Power Platform Admin Center. Every agent should have a maximum monthly credit allocation based on its cost class. Bronze agents get tight caps. Silver agents get moderate caps. Gold agents get higher caps but still have a ceiling. When an agent hits its cap, it stops responding or falls back to a static FAQ. This prevents runaway agents from consuming unlimited credits during a traffic spike or a loop bug. Azure API Management provides the technical enforcement layer. You can apply rate limiting and quota policies by cost class at the gateway. Gold workloads get higher tokens per minute limits. Bronze workloads get throttled first when the gateway is under pressure. You can also enforce max tokens limits by policy, preventing any agent from generating unexpectedly long responses that blow the output budget. These policies are not suggestions. They are rules that the infrastructure enforces. The combination of budgets, caps, and rate limits creates a layered defense. Finance owns the budget. Platform teams own the gateway policies. App teams own the agent design. When a spike happens, the budget alert fires first. If the spike continues, the credit cap kicks in. If the spike is a sustained change in demand, the rate limit smooths the load. And if none of these catch it, the cost class classification ensures that the most expensive workloads were already the smallest segment of your traffic. These guardrails also change behavior. When app teams know that bronze agents have a 200 token max response limit, they design for conciseness. When they know that silver agents must use cached responses for the top 10 FAQ questions, they build caching into the flow from day one. Governance is not a constraint. It is a design specification, and when it is enforced automatically, it becomes part of the architecture rather than an afterthought. The 90-day implementation roadmap. Theory is useful, but what matters is execution. The following roadmap breaks the entire framework into 3 30-day sprints. Each sprint has a clear deliverable, exit criteria, and rollback triggers. Do not skip the audit sprint. Do not deploy caching without validation. And do not commit to PTU before you have 30 days of real telemetry. The organizations that fail this transition are the ones that treat it as a configuration change rather than an architecture program. days 1 through 30, the audit sprint. The goal of the first sprint is visibility, because you cannot optimize what you cannot see, and right now most organizations are flying blind. Week 1 is tagging cleanup. Every Azure OpenAI resource, every Copilot Studio environment, and every related infrastructure component gets tagged with 4 mandatory fields: environment, department, agent name, and cost class. If a resource already exists without tags, retroactively apply them based on ownership records or deployment logs. This is tedious. It is also non-negotiable. Every cost query, every KQL analysis, and every chargeback report depends on these tags being clean and consistent. Week 2 is logging enablement. Turn on diagnostic logging for every Azure OpenAI deployment and stream the logs to a log analytics workspace. If you have Azure API management in front of your endpoints, enable trace logging there as well. In Copilot Studio, export the built-in analytics to a Dataverse table or a Power BI dataset. The specific telemetry you need is input tokens per request, output tokens per request, model SKU, latency, and user session ID. Without session ID, you cannot attribute cost to specific conversation patterns. Week 3 is baseline construction. Run your first KQL query against the log analytics workspace to compute average tokens per interaction, peak tokens per interaction, and total interactions per day for each tagged agent. Run the Copilot Studio consumption estimator for every active agent. Record the projected credit need versus current pack size. And run your first Azure Copilot natural language cost query. Summarize my AI spend by service and tag for the last 30 days. Store all of this in an Azure Monitor workbook that the platform team, finance, and app teams can all access. Week 4 is anomaly identification. Compare the last 30 days of spend against the prior 30 days. Flag any agent whose cost per interaction increased more than 20% week over week. Investigate the top 3 drivers. Common culprits are a new feature that increased retrieval scope, a marketing campaign that drove traffic to an unoptimized agent, or a code change that removed a max tokens limit. Document the root cause for each anomaly. These become your first optimization targets in Sprint 2. The exit criteria for Sprint 1 are simple. You must have clean tags on 100% of resources. You must have 30 days of diagnostic logs in a queryable workspace. You must have a baseline workbook showing cost per interaction, tokens per interaction, and P95 latency for every agent. And you must have an anomaly log with at least 3 investigated spikes. If you cannot produce these artifacts, do not proceed to Sprint 2. You are not ready to optimize. Days 31 through 60, the quick win sprint. The goal of the second sprint is 20 to 30% cost reduction with zero quality degradation. These are the low-hanging fruits that require minimal architectural change but deliver immediate impact. Week 5 is semantic caching deployment. Identify your top 5 most repeated query patterns. These are usually FAQ questions, policy lookups, and status checks. For each pattern, deploy semantic caching through Azure API management using the policy pair we discussed earlier. Set an initial similarity threshold of 0.94. Test with real user queries and measure cache hit rate. If hit rate is below 30% after 1 week, lower the threshold to 0.92. If false positives appear, raise it back. Target a cache hit rate of 40% or higher for these top 5 patterns. That alone eliminates 40% of LLM calls for your most common traffic. Week 6 is max tokens enforcement. Review every agent and enforce a max tokens limit based on cost class. Bronze agents get a 100 token output limit. Silver agents get a 200 token limit. Gold agents get a 500 token limit with a requirement that the app team justifies any exception. This is not about restricting users. It is about forcing agents to be concise. If an answer genuinely needs more than 200 tokens, the agent should offer a summary and invite the user to ask for details. Most users prefer concise answers anyway. Week 7 is retrieval tuning. For every RAG-based agent, reduce the top K retrieval count from its current default to 7 chunks maximum. Enable hybrid search with semantic ranking if it is not already active. Rechunk long documents using paragraph boundaries rather than fixed token counts. And add metadata filters so that queries about HR policy only search HR documents, not the entire corporate knowledge base. These changes reduce input tokens before they ever reach compression or caching. Week 8 is budget alert activation. Set Azure cost management budgets at the tenant level and at the department level. Configure the 50, 80, 100 alert ladder. Set Copilot Studio credit caps for every bronze and silver agent, and add APIM rate limit policies that throttle bronze workloads when gateway capacity reaches 80%. Test the alert chain by simulating a traffic spike in your staging environment. Verify that alerts fire, logic apps trigger, and throttling engages at the correct threshold. The exit criteria for Sprint 2 are measurable. You must demonstrate a 20% reduction in average tokens per interaction. You must demonstrate a 15% reduction in cost per interaction. Cache hit rate must exceed 40% for the top 5 patterns, and no alert or cap must have fired accidentally during normal operations. If you hit these numbers, you have proven that cost control does not require quality sacrifice. If you do not hit these numbers, do not proceed. Investigate why. Days 61 through 90, the architecture sprint. The goal of the third sprint is structural transformation. The quick wins are exhausted, so now you redesign the pipeline, starting with LLM Lingua deployment in week 9. Choose one high-volume silver or gold agent with long-retrieved documents. Deploy LLM Lingua 2 from the Azure AI model catalog as a pre-processing step in prompt flow. Start with a 30% compression target. Run an A/B test using Azure AI Studio evaluations. Compare the compressed path against the uncompressed path on 3 metrics: answer accuracy, user satisfaction, and token cost. If accuracy drops more than 2%, reduce compression. If accuracy holds, increase to 50%. Document the optimal compression ratio and apply it to all similar agents. Week 10 is model routing deployment. In Azure AI Foundry, deploy the model router. Redirect one non-regulated bronze or silver agent to the router endpoint. Monitor aggregate KPIs for 1 week, cost per request, P95 latency, and escalation rate. Compare against the prior week when the agent used GPT-5 Global directly. If cost per request drops by 40% or more with no latency or quality degradation, expand routing to additional agents. If KPIs degrade, investigate whether the router is sending complex queries to a model that is too small. You may need to tune the prompt or add task type hints to improve routing accuracy. Week 11 is PTU evaluation. Using the telemetry from the last 30 days of Sprint 2 and Sprint 3, compute your sustained utilization for any agent that is a candidate for yearly PTU. The formula is simple. Divide your actual average tokens per minute by the PTU capacity you would reserve. If the result is 86% or higher and the workload is mission critical with stable demand, evaluate a yearly PTU commitment. If the result is below 80%, stay on PAYG. Do not let procurement pressure you into a commitment to get a discount. An underutilized PTU is more expensive than PAYG with caching. Week 12 is governance hardening. Publish the cost class criteria in your internal wiki or developer portal. Create an onboarding checklist that every new agent must complete before deployment. The checklist includes cost class justification, max token setting, cache configuration, model assignment or router endpoint, and credit cap. Train citizen developers on the framework. Most cost overruns come from well-meaning developers who simply do not know that a cheaper model exists or that retrieval scope matters. Education is cheaper than remediation. The exit criteria for Sprint 3 are architectural. You must have at least one agent running with semantic caching and validated hit rates. You must have at least one agent running with LLM Lingua compression and proven accuracy. You must have at least one agent routed through the Azure AI Foundry model router with stable KPIs. You must have a published cost class framework and an onboarding checklist. And you must have a PTU evaluation for every gold candidate, even if the conclusion is to stay on PAYG. Rollback triggers and risk mitigation. Every sprint includes a rollback plan. If cache hit rates drop below 20% after deployment, disable the cache and investigate. If LLM Lingua compression degrades user satisfaction by more than 5%, revert to the uncompressed path and retune. If model routing increases escalation rates, fall back to direct model deployment and engage Microsoft support to review the router behavior. If a budget alert fires because of a genuine business surge rather than waste, temporarily raise the cap and schedule a capacity review. The biggest risk is organizational fatigue. A 90-day program requires dedicated time from platform engineering, app teams, and finance. If your organization cannot sustain the pace, extend the timeline, but do not skip steps. An audit without action is useless. Quick wins without architecture are temporary, and architecture without governance will erode within 6 months as new teams join and old habits return. The second biggest risk is scope creep. This roadmap is about cost architecture, not feature development. Do not add new agent capabilities during the 90 days unless they are specifically designed to test the cost framework. Do not redesign your knowledge base unless the retrieval tuning in week 7 requires it. Stay focused. The organizations that succeed treat this as a capital program with a defined budget, a defined timeline, and a defined return on investment. The governance model. A 90-day roadmap delivers a cost-optimized architecture, but architecture erodes without governance. As new teams join, citizen developers experiment, and procurement renews licenses without checking utilization. Within 6 months, the agents you optimized are surrounded by new agents built on old habits. Governance is the operating model that prevents this erosion. It is not bureaucracy, it is the system that keeps the architecture alive. The governance model has 3 layers. The platform team owns the infrastructure and the standards. The app teams own the agents and the user experience. And finance owns the budget and the chargeback. Each layer has clear responsibilities, clear metrics, and clear escalation paths. When these layers are aligned, cost control becomes self-sustaining. When they are not aligned, every optimization is eventually undone. The platform team. The platform team is the center of gravity. They own the Azure OpenAI deployments, the Azure API management instance, the model router, the LLM Lingua endpoints, and the Azure Monitor workbooks. They publish a service catalog that defines what every app team can use and how to request it. The service catalog has 4 entries. Entry 1 is bronze hosting. This includes a shared Azure OpenAI deployment on PAYG APIM with rate limiting, a cached FAQ backend, and a model router endpoint. Bronze workloads are automatically throttled and capped. Entry 2 is silver hosting. This includes a dedicated PAYG deployment, semantic caching, LLM Lingua compression, and higher rate limits. Silver workloads are reviewed quarterly for cost drift. Entry 3 is gold hosting. This includes a dedicated PTU or high-capacity PAYG deployment, custom retrieval tuning, direct model assignment, and SLA-backed latency. Gold workloads require a business case, a named SLA, and a cost justification that is renewed every 6 months. Entry 4 is the sandbox. This is the only environment where app teams can experiment freely. It uses the cheapest models, the strictest rate limits, and a weekly credit cap that resets every Monday. Experiments that outgrow the sandbox must graduate to bronze, silver, or gold via a platform review. Nothing lives in the sandbox permanently. The platform team also owns the cost dashboard. This dashboard shows real-time spend by cost class, by department, and by agent. It highlights anomalies automatically. It tracks cache hit rates, compression ratios, routing accuracy, and PTU utilization, and it is the single source of truth for every cost review meeting. If an app team disputes a charge, the platform team points to the dashboard. If finance questions a spike, the platform team pulls the telemetry. There are no debates about who used what because the data is public. The app teams. App teams do not choose their infrastructure, they choose their use case, and the use case determines the cost class. Before any new agent is built, the app team completes a brief intake form. The form asks 5 questions. What is the user-facing goal? What is the expected monthly interaction volume? What knowledge sources are required? What is the acceptable latency? And what is the business impact if the agent fails or returns a wrong answer? The answers determine the cost class. If the agent is customer-facing and failure costs revenue, it is a gold candidate. If it is internal and failure causes minor inconvenience, it is silver. If it is experimental or low stakes, it is bronze. The platform team reviews the intake and assigns the infrastructure tier. App teams can appeal, but they need data. If a bronze agent is missing its latency target, the app team can request silver resources. But they must show that the latency problem is infrastructure bound, not design bound. Most latency problems are design bound. App teams also own user experience quality. They monitor escalation rates, user satisfaction scores, and answer accuracy. If a bronze agent has high escalation rates, the app team must improve the retrieval tuning or the prompt design before requesting a more expensive model. Throwing GPT-5 Global at a bad prompt does not fix the prompt. It just makes the bad prompt expensive. The intake form also includes a cost estimate. Using the Copilot Studio consumption estimator and the Azure pricing calculator, the app team projects their first month cost. This projection is compared against actual spend after 30 days. If actual spend exceeds the projection by more than 50%, the platform team initiates a review. This prevents the all-too-common pattern where an experiment is approved as low cost and then silently balloons into a production dependency. Finance and chargeback. Finance owns the budget and the chargeback model. The chargeback model is simple. Every app team pays for the tokens and credits their agents consume. There is no shared pool that hides individual accountability. If the HR team builds an agent that consumes $10,000 per month, the HR budget sees $10,000. If the support team builds an agent that consumes $500 per month, the support budget sees $500. This sounds harsh, but it is the only way to align incentives. When costs are hidden in a central platform budget, app teams have no reason to optimize. When costs are visible in their own P&L, optimization becomes a priority. And the platform team supports this by providing detailed chargeback reports from the cost dashboard. Every line item is tagged with agent name, department, and cost class. Finance does not need to guess. They just need to read. Finance also owns the annual planning cycle. Every year, each app team submits a forecast for agent growth, model upgrades, and capacity changes. The platform team translates these forecasts into Azure OpenAI PTU needs, Copilot Studio pack sizes, and infrastructure scaling plans. Finance reviews the total and either approves the budget or challenges the forecasts. This is standard capital planning. The only difference is that the inputs are tokens and credits instead of servers and storage. The quarterly business review is where all 3 layers meet. Platform presents the dashboard. App teams present their quality metrics. Finance presents the budget variance. Together, they decide whether any gold workloads should be reclassified to silver, whether any silver workloads should graduate to gold, and whether any bronze experiments should be retired. These decisions are data-driven and public. There are no hidden negotiations. Anti-patterns to avoid. There are 4 common governance failures that undo cost architecture. The first is the hero team. A high-performing app team builds a successful agent, gets promoted, and leaves behind a mess of untagged resources, undocumented prompts, and hard-coded model references. The fix is simple. No agent graduates from sandbox to production without platform review. Success does not exempt a team from standards. The second is the finance override. Finance sees a high bill and demands immediate cuts. They cap all agents indiscriminately or cancel all PTU reservations. This destroys user experience and damages business value. The fix is the cost class framework. Finance can challenge gold classifications, but they cannot throttle gold workloads that have approved SLAs, and they cannot cancel PTU reservations for stable production workloads without a migration plan. The third is the platform monopoly. The platform team becomes so controlling that app teams bypass them entirely and build shadow agents in personal Azure subscriptions or unmanaged Copilot Studio environments. This is the most expensive outcome of all because shadow agents have zero visibility. The fix is service catalog speed. Platform reviews must happen within 48 hours. Sandbox provisioning must be self-service, and the published standards must be clear enough that app teams do not need to negotiate every detail. The fourth is the permanent pilot. An agent is built as a pilot, consumes seeded credits, and never gets reviewed because it is just an experiment. After November 2026, these permanent pilots become permanent bills. The fix is a sunset clause. Every sandbox agent expires after 90 days unless it is promoted to bronze or higher. Every bronze agent is reviewed annually, and every agent without an owner is deleted. Success metrics. Governance success is measured by drift. Cost drift is the percentage increase in spend per interaction month over month. A well-governed environment shows flat or declining cost per interaction. Architecture drift is the percentage of agents that deviate from their assigned cost class. A well-governed environment shows near zero architecture drift. And behavior drift is the percentage of new agents that bypass the intake process. A well-governed environment shows zero behavior drift. If all three drift metrics are near zero, your governance model is working. If any metric spikes, you have a gap. Find it, fix it, and move on. Governance is not a one-time project. It is a continuous process of detection and correction. And like the architecture it protects, it is only as strong as the attention you give it. The 2026 calendar and what to watch. Architecture and governance are not static. Microsoft changes pricing, models, and credit policies. Your environment changes as new agents are built, old ones retire, and user behavior shifts. The final piece of this framework is a calendar, a set of recurring checks that keep your cost architecture current. The November 2026 deadline. The most urgent calendar item is November 1st, 2026. On that date, Microsoft removes seeded AI Builder credits from all tenants. Every organization that has been relying on Power Apps Premium or Dynamics 365 licenses to cover AI Builder and Copilot Studio usage will see an immediate cost increase. Your preparation should start no later than August 1st, 2026. By then, you must have a complete inventory of every agent, every flow, and every experiment that currently consumes seeded credits. For each one, decide whether to migrate to Copilot Studio capacity packs, migrate to Azure AI architectures, or retire. Do not wait until October. Procurement lead times for capacity packs can be several weeks, and re-architecting an agent from Copilot Studio to Azure AI is not a weekend project. By September 1st, you should have purchased the initial capacity packs and set up PAYG overflow billing. Test the billing chain by running synthetic traffic through a non-production agent and verifying that credits are consumed in the correct order. Seeded first, then packs, then PAYG. If the order is wrong, open a support ticket immediately. Billing misconfiguration is easier to fix before the deadline than after. By October 1st, communicate the change to all citizen developers and app teams. Show them the new cost per interaction. Show them the credit caps. And show them the retirement plan for any agents that do not justify the new cost. Some experiments will not survive. That is the point. The free period created value, but it also created waste. November is when you separate the two. Quarterly reviews. After the November transition, run a formal cost architecture review every quarter. The review has a fixed agenda and should take no more than 90 minutes. First 15 minutes, platform team presents the cost dashboard. Show spend by layer, by cost class, and by department. Highlight any month-over-month variance above 10%. Call out cache hit rate trends, compression ratios, and routing accuracy. Next 30 minutes, app teams present agent quality metrics. Show escalation rates, user satisfaction, and accuracy scores. Compare these against the prior quarter. If quality improved while cost declined, celebrate. If quality declined while cost declined, investigate. You may have over-optimized. Next 30 minutes, finance presents budget variance and chargeback reconciliation. Confirm that every department is billed correctly. Identify any shadow spending or untagged resources, and update the annual forecast based on actual growth. Final 15 minutes. Decisions. Promote any silver agent that has outgrown its tier and justified the business case. Demote any gold agent that is missing its SLA or running below target utilization. Retire any bronze agent that has not been used in 60 days. And update the service catalog if new Azure features change the economics. Monthly monitoring. Between quarterly reviews, run a lightweight monthly check. It takes 30 minutes and covers 5 questions. Check whether any agent is consuming more than 120% of its credit cap, whether any Azure OpenAI deployment is showing utilization above 80% or below 20%, whether cache hit rate is stable, whether LLM Lingua compression ratio is stable, and whether any new model releases in the Azure AI Foundry catalog could change routing economics. The last question is often overlooked. Microsoft adds new models to the router pool and the model catalog without fanfare. A new model that is cheaper than GPT-5 Mini for your specific task could drop your per request cost by another 20%. But you will only know if you are watching. Subscribe to the Azure AI release notes, review the model catalog monthly, and test promising new models in the sandbox before promoting them to production. The annual cycle. Once per year, typically in January or February, run a full architecture refresh. Review every agent from scratch. Revalidate the cost class of every production workload. Rerun the PTU versus PAYG analysis for all gold candidates using the last 12 months of telemetry. Update the baseline workbook with new P95 values, and refresh the training materials for citizen developers. This annual cycle is also when you negotiate capacity pack sizes and PTU reservations for the coming year. Use your actual consumption data, not your projected growth, as the starting point. If you grew 20% last year, plan for 20% growth next year. Do not let vendor forecasts or executive ambition inflate your commitments. An overcommitted PTU reservation is a stranded asset, and an undercommitted capacity pack plan leads to expensive PAYG overflow. The final annual task is a vendor check. Review Microsoft's published pricing for Azure OpenAI, Copilot Studio, and Azure AI Foundry. Note any changes that took effect in the prior year. Model prices, credit costs, and PTU rates all change. If you are not tracking these changes, your baseline is wrong and your forecasts are useless. Update your cost dashboard with the current rates before you build next year's budget. What to watch in 2027 and beyond. The AI cost landscape will not stabilize in 2026. Model prices will continue to fall as competition increases and hardware improves. Context windows will grow, which could increase prompt costs unless compression and caching keep pace. And autonomous agents will become more capable, which could increase consumption unless governance caps keep pace. The organizations that thrive are the ones that treat cost architecture as a core competency, not a one-time project. They have teams, processes, and calendars dedicated to monitoring and optimization. They do not wait for the invoice to surprise them. They see the trend in their dashboard and adjust before the trend becomes a crisis. That is the final principle. Cost architecture is not a destination. It is a discipline. And in the Microsoft cloud, where the boundary between licensed and consumed is blurry and moving, discipline is the only protection against runaway spend. Cost architecture beats cost accounting every time. Start your audit this week because November is coming, and every experiment you build for free is about to start charging. Case study: rebuilding the Contoso support agent. Theory is clearer with an example. This case study is a composite based on patterns I have seen across multiple Microsoft environments. The company, the numbers, and the timeline are representative. The decisions are real. The starting point. Contoso has a customer support agent built in Copilot Studio. It answers questions about product features, troubleshooting steps, and warranty status. The agent is connected to a SharePoint knowledge base with roughly 5,000 articles. It uses Azure AI Search for Retrieval and Azure OpenAI GPT-5 Global for response generation. The agent handles roughly 50,000 conversations per month. In January 2026, the support team receives the first consolidated Azure invoice that includes the full agent cost. The total is $48,000 for the month. The support director assumes it is a mistake. It is not. Breaking down the $48,000 reveals the 3 hidden taxes in action. The context tax accounts for roughly $22,000. The agent retrieves 30 chunks per query at an average of 600 tokens each. With 50,000 conversations averaging 3 turns each, that is 150,000 retrievals per month. At GPT-5 global input pricing, the retrieval context alone consumes $22,000 before the user question is even processed. The reasoning tax accounts for roughly $18,000. Every query, from simple FAQ to complex troubleshooting, is routed to GPT-5 Global. Roughly 70% of the queries are simple enough for GPT-5 Mini or GPT-5 Nano. But the agent has no routing logic, so everything runs at the flagship rate. The output tokens, which are 8 times more expensive than input tokens, drive most of this cost because the model generates long, detailed responses even for one-sentence questions. The autonomous tax accounts for the remaining $8,000. The agent is configured to proactively check order status for every returning customer, triggering a Power Automate flow that queries Dataverse and the Microsoft Graph. This feature seemed helpful during design. In practice, it consumes 10 Copilot credits per proactive check. And with 20,000 returning customers per month, that is 200,000 credits. At 1 cent per credit on PAYG, that is $2,000. The remaining 6,000 comes from Azure infrastructure, logging, and data egress that were never modeled during the pilot phase. The audit phase. The support team engages the platform team to run the audit sprint. They clean up tags, enable diagnostic logging, and build the token flow map. The map confirms what the invoice suggested. The retrieval layer is the biggest problem, followed by the model layer, followed by the proactive automation. The baseline workbook shows an average cost per interaction of 96 cents. For comparison, a human support agent costs roughly $8 per interaction when fully loaded. So the agent is still cheaper than humans, but it is 10 times more expensive than it needs to be. And with planned growth to 200,000 conversations per month, the projected annual cost would exceed $1 million. That is no longer a support tool. That is a budget line item that competes with headcount. Sprint 2, the quick wins. In February, the team deploys semantic caching for the top 10 FAQ questions. These questions account for roughly 45% of all queries. The cache is implemented in Azure API management with a similarity threshold of 0.94. Within 2 weeks, cache hit rate stabilizes at 52%. That eliminates roughly 26,000 LLM calls per month. The immediate saving is $12,000. At the same time, the team enforces max tokens limits. Bronze class queries, which include all FAQ and simple status checks, are capped at 120 tokens. Silver class queries, which include standard troubleshooting, are capped at 250 tokens. Only gold class queries, which require multi-step reasoning across documents, are allowed 500 tokens. The average output length drops from 300 tokens to 180 tokens. This saves roughly $6,000 per month in output tokens alone. The team also tunes retrieval. Top K is reduced from 30 chunks to 5. Hybrid search with semantic ranking is enabled, and metadata filters are added so that warranty queries only search warranty articles and troubleshooting queries only search troubleshooting guides. The average retrieved context drops from 18,000 tokens per query to 4,000 tokens. This saves roughly $9,000 per month. By the end of February, the monthly cost has dropped from $48,000 to $21,000. The cost per interaction has dropped from 96 cents to 42 cents. And user satisfaction has actually improved slightly because the shorter answers are more focused and the tuned retrieval returns more relevant context. Sprint 3, the architecture shift. In March, the team deploys LLM Lingua compression on the silver and gold retrieval paths. Compression targets 40% on average. Some dense technical documents compress by 60%, some sparse policy documents compress by only 25%. The A/B test shows no measurable degradation in answer accuracy or user satisfaction. The compression saves roughly $3,000 per month in input tokens. The team also deploys the Azure AI Foundry model router. Bronze queries are routed to GPT-5 Nano. Silver queries are routed to GPT-5 Mini. Only gold queries reach GPT-5 Global. The router adds a small latency overhead of roughly 50 milliseconds per call, which is invisible to users. The cost saving is $7,000 per month. Combined with the other optimizations, the total monthly cost is now $11,000. The team evaluates PTU for the gold workload. The gold queries represent roughly 5% of traffic but still run on GPT-5 Global. The average utilization of a candidate PTU would be 72%. That is below the 86% break-even threshold. The team stays on PAYG. They also enable prompt prefix caching for the gold system prompt, which reduces the effective input cost by roughly 15%. The governance lock-in. By April, the architecture is optimized, but the team knows that without governance, the costs will creep back. They implement the full framework. The support agent is classified as silver with gold escalation. The cost dashboard is published. The app team reviews it weekly. And finance sees a chargeback of $11,000 per month instead of $48,000. The annual projection is now $132,000 instead of $1 million. The support director no longer sees the agent as a budget risk. They see it as a scalable asset. And the platform team uses the Contoso case as the template for every new agent request in the organization. This is what cost architecture delivers. Not incremental savings, but structural transformation. From 48,000 to 11,000, from guessing to measuring, and from reactive panic to proactive design. The anti-patterns most teams miss. Even teams that follow the framework make mistakes. Here are the 5 anti-patterns I see most often and how to avoid them. Anti-pattern 1. The forever context window. Some teams think that keeping the entire conversation history improves user experience, so they append every prior turn to every new prompt. After 10 turns, the prompt is longer than the retrieval context. And the model is paying for the same chat history on every call. The fix is conversation summarization. After every 3 turns, summarize the conversation into a single paragraph of key facts and user intent. Then drop the raw turns. The model still knows what the user wants, but the token count drops by 80%. This is especially important for multi-turn support agents and interview-style bots. Anti-pattern 2, the vanity metric dashboard. Teams love to build dashboards that show total requests, total users, and total conversations. These are vanity metrics. They tell you that the agent is popular. They do not tell you whether it is efficient. The metrics that matter are cost per interaction, tokens per interaction, cache hit rate, compression ratio, routing accuracy, and cost drift. If your dashboard does not show these 6 numbers for every agent, it is a popularity contest, not a cost control tool. Fix it. Anti-pattern 3, the model upgrade trap. Microsoft releases new models every quarter. Teams immediately upgrade to the latest flagship because it scores better on benchmarks. They do not ask whether their specific tasks need the improvement. For most FAQ, classification, and extraction workloads, the difference between GPT-4 and GPT-5 is invisible to users, but the cost difference is very visible to finance. The rule is simple. Only upgrade the model if your evaluation suite shows a measurable improvement in your specific task, not on general benchmarks, on your task. If the improvement is less than 5% and the cost increase is 25%, the upgrade is a bad deal. Anti-pattern 4, the capacity pack guessing game. Teams buy Copilot Studio capacity packs based on fear. They buy 10 packs because they are afraid of running out, then use only 4. The unused credits expire every month. That is 6 packs of waste, or $1,200 per month in dead money. The fix is to start with PAYG for the first 30 days. Measure actual consumption, then size your packs to cover 120% of your observed average. Not your projected peak, your observed average. Use PAYG for the rest. This gives you a predictable baseline and a variable overflow. It is the same principle as PTU plus PAYG in Azure OpenAI. Anti-pattern 5, the governance bypass. A platform team builds a beautiful service catalog and a rigorous intake process. Then a senior executive wants a quick demo for a board meeting. The executive's assistant spins up a new agent in a personal sandbox, connects it to a production knowledge base, and shows it at the meeting. The agent is never reviewed, never classified, and never capped. 6 months later, it is still running and consuming credits. The fix is technical, not procedural. Every production knowledge base should require platform authentication. Every Azure OpenAI deployment should be behind APIM with rate limits. And every Copilot Studio environment should have a tenant-level credit cap that no individual user can override. If the architecture enforces the rules, the bypass is impossible. If the architecture allows the bypass, no policy will stop it. The final anti-pattern, perfection paralysis. Some teams never deploy because they are afraid of getting it wrong. They want to model every scenario, forecast every edge case, and build the perfect architecture before they launch a single agent. They spend 6 months planning and never save a dollar because nothing is live. The framework is designed to avoid this. Sprint 1 is an audit, not a design. Sprint 2 delivers quick wins in 30 days. Sprint 3 builds the architecture on top of a working baseline. You do not need perfection, you need progress. Start the audit this week. Deploy caching next week, the rest follows. Advanced scenarios, multi-tenant, multi-region, and hybrid workloads. The core framework applies to single-tenant, single-region deployments. But most enterprise Microsoft environments are more complex. They serve multiple business units, span multiple geographies, and combine low-code Copilot Studio agents with pro-code Azure architectures. These complexities do not change the principles. They change the implementation. Multi-tenant cost isolation. In a multi-tenant SaaS product, each customer shares the same underlying infrastructure, but should see separate cost accounting. Without isolation, one customer's surge becomes everyone else's bill, and without chargeback, you cannot price your product correctly. The solution is per-tenant routing at the gateway. Azure API Management supports tenant-specific API keys and subscription quotas. Each tenant gets a key that maps to a dedicated rate limit, a dedicated cache partition, and a dedicated cost tag. The logs show exactly which tenant consumed which tokens. The chargeback is automatic. For caching, each tenant needs its own cache partition. A semantic cache that mixes tenant A's healthcare queries with tenant B's financial queries is a privacy risk and a quality risk. Use Redis cache keys that include the tenant ID. The router still works, the compressor still works, but the cached responses are never shared across tenants. For model routing, you may want tenant-specific routing profiles. A healthcare tenant might require GPT-5 Global for compliance reasons. A retail tenant might be fine with GPT-5 Mini. The Azure AI Foundry model router does not support tenant-specific pools today, so you may need a custom orchestrator layer. The orchestrator inspects the tenant ID and routes to the appropriate deployment. This adds complexity, but it is the only way to satisfy mixed compliance requirements. Multi-region latency and cost trade-offs. Azure OpenAI pricing varies by region. East US is often cheaper than West Europe, but your users in Germany do not want their data processed in Virginia. Data residency requirements, latency requirements, and cost requirements often conflict. The standard pattern is a hub-and-spoke architecture. The primary region hosts the gold workloads, the centralized cache, and the governance dashboard. Secondary regions host bronze and silver workloads close to the users. Azure Front Door routes traffic by geography, sending European users to West Europe and Asian users to Southeast Asia. Each region has its own APIM instance, its own cache, and its own rate limits. The cost optimization is regional capacity planning. If your West Europe traffic is steady and high, a yearly PTU in West Europe may make sense for gold workloads. If your Southeast Asia traffic is spiky and unpredictable, PAYG is better. Do not apply the same capacity strategy to every region. each region gets its own analysis. The telemetry aggregation is harder in multi-region setups. You need a central log analytics workspace that ingests logs from all regional deployments. Use Azure Monitor cross-resource queries to compute global cost per interaction, regional cost per interaction, and inter-region data transfer costs. Data egress between regions is often overlooked and can add 5 to 15% to the total bill. Hybrid low-code and pro-code. Most large Microsoft environments are not purely Azure AI Foundry or purely Copilot Studio. They are hybrid. Copilot Studio handles the low-code, business-led agents. Azure AI Foundry handles the pro-code, engineering-led agents, and Power Automate connects the two. The cost danger in hybrid environments is double billing. A Copilot Studio agent that calls a custom Azure function, which then calls Azure OpenAI, might be billed in both places. The Copilot Studio agent consumes credits for the action call, the Azure function consumes Azure compute and storage, and the Azure OpenAI deployment consumes tokens. If you are not tagging the Azure function and correlating its logs with the Copilot Studio session, you will see two separate line items and never know they belong to the same user request. The fix is end-to-end correlation IDs. Every user session gets a unique correlation ID. The Copilot Studio agent passes it to the Azure function. The Azure function passes it to Azure OpenAI. Every log entry includes the correlation ID. Then your KQL queries can join the logs across services and compute the true end-to-end cost per interaction. Without correlation IDs, hybrid cost analysis is impossible. Another hybrid danger is model inconsistency. A Copilot Studio agent might use GPT-5 Global through the built-in generative answers feature. A pro-code agent in the same organization might use GPT-5 Mini through Azure AI Foundry. They serve the same user base with the same questions, but one costs 8 times more per token. The governance fix is the service catalog. Every agent, regardless of platform, must register its model assignment. The platform team reviews quarterly and consolidates where possible. Seasonal and event-driven spikes. Some workloads are not steady because retail agents spike in November, tax agents spike in March, and event-driven agents spike when a product launches or a crisis hits. Steady-state architecture fails for these patterns. The solution is elastic throttling combined with burst PAYG. Maintain a small PTU or capacity pack for baseline demand, then use PAYG for the spikes. In Azure API management, configure burst policies that allow temporary traffic increases of 200 to 500% for a limited time window. After the window, traffic falls back to the baseline rate limit. Also, pre-warm your cache before predictable spikes. If you know that Black Friday will generate a surge of the same 20 questions, pre-populate the semantic cache with those answers. You can do this by running a script that sends the top 20 queries through the APIM endpoint a few hours before the spike. The cache is warm, and the real user traffic hits cached responses instead of the LLM. For unpredictable spikes, the safeguard is the budget alert at 50%. If a surprise event drives traffic up, the alert fires before the bill explodes. The platform team can then temporarily promote the agent to a higher tier, increase the rate limit, or add emergency PAYG capacity. The key is that the response is triggered by data, not by an angry finance email 2 weeks later. The governance scaling rule. As your environment grows from 10 agents to 100 agents, governance must scale without creating a bottleneck. The 100 agent milestone is where many organizations fail. The platform team cannot review every agent personally, the finance team cannot negotiate every capacity pack individually, and the app teams cannot wait 2 weeks for sandbox approval. The scaling rule is automation and self-service. The intake form becomes a web app that validates cost class automatically based on the 5 questions. The service catalog becomes a Terraform or Bicep template repository that provisions approved infrastructure in minutes. The cost dashboard becomes a Power BI report that auto-refreshes, and the quarterly review becomes a 30-minute stand-up where only exceptions are discussed. What does not scale is personal approval. If every agent requires a meeting, the system breaks at 50 agents. Design your governance for 100 agents on day 1. Even if you only have 5 agents today, the processes you build now determine whether you can grow later. The emergency brake. When costs spiral, no matter how well you architect, surprises happen, such as an agent going viral on social media, a marketing campaign driving 10 times expected traffic, or a code bug creating an infinite loop that burns tokens at midnight. You need an emergency brake that stops the spend before it becomes a career event. The first brake is the Azure API Management Circuit Breaker. Configure a policy that detects error rates or latency spikes above a threshold and automatically returns a static fallback response. If your agent normally responds in 2 seconds and suddenly starts timing out at 30 seconds, something is wrong. The circuit breaker stops the bleeding and alerts the platform team. The second brake is the Copilot Studio Emergency Cap. In addition to the standard monthly credit cap, set a daily cap at 50% of the monthly budget. If an agent consumes its entire daily allocation by noon, it shuts down for the rest of the day. Users see a polite message explaining that the service is temporarily unavailable. This is not ideal user experience, but it is far better than a $10,000 surprise. The third break is the Azure budget hard limit. While most budgets are set to alert, you can configure some budgets to trigger automation. A Logic app can receive the 100% budget alert and execute a runbook that disables non-essential agent deployments, scales down Azure OpenAI endpoints, or redirects traffic to a static FAQ page. This is the nuclear option, so use it only for truly catastrophic scenarios, but know that it exists. The fourth break is human judgment. Every platform team needs an on-call rotation with the authority to throttle or disable agents. The authority must include the ability to override app team objections in real time. If a bug is burning $5,000 per hour, the platform engineer must be able to pull the plug without waiting for a change advisory board meeting. Document this authority, train the engineers, and practice the scenario in a tabletop exercise before it happens for real. The final break is post-incident learning. After every cost spike, run a blameless post-mortem. Ask what happened, why the monitoring did not catch it sooner, and what architectural change would prevent a recurrence. Update the runbook, update the alert thresholds, and share the learnings across all app teams. A spike that teaches the organization is expensive but valuable. A spike that repeats because nobody learned is just waste. The weekly measurement checklist. Cost architecture is not a set-and-forget system. It requires weekly attention for the first 90 days, then monthly attention thereafter. The following checklist takes 15 minutes and should be completed by the platform team lead every Monday morning. First, check the cost dashboard. Verify that total AI spend is within 5% of the prior week. If it is higher, drill down by agent. If a single agent caused the jump, open a ticket with the app team owner. If the jump is broad-based, check whether a new model or a new feature was deployed. Second, check cache hit rates. Semantic caching should deliver 40% or higher for mature agents. If hit rate drops, investigate whether the user question patterns have changed. A new product launch or a policy change can shift the question distribution and invalidate your cached answers. Third, check LLM Lingua compression ratios. The ratio should be stable within 10% week over week. If compression drops, the input documents may have changed. New document types, longer paragraphs, or denser technical content can reduce compressibility. Retune the compression target if needed. Fourth, check model routing accuracy. Review the aggregate cost per request and the P95 latency. If cost per request rises while volume stays flat, the router may be sending more queries to expensive models than before. This can happen if user questions become more complex, or if a prompt change made the queries look more difficult to the router. Fifth, check credit caps and rate limits. Verify that no agent hit its cap unintentionally. If an agent hit its cap 3 weeks in a row, either the cap is too low or the agent is growing organically. Either way, schedule a review. Sixth, check for new resources that lack tags. Any Azure OpenAI deployment, any Copilot Studio environment, or any APIM instance created in the last week should have the mandatory tags. Untagged resources are invisible to chargeback and cost control. Tag them immediately or delete them if they are unauthorized. Seventh, review the upcoming calendar. Check for any product launches, marketing campaigns, or seasonal events this week that could drive traffic. If there are, verify that the cache is pre-warmed, the rate limits are adjusted, and the budget alert thresholds are temporarily lowered for closer monitoring. Eighth, verify that no new models were added to the Azure AI Foundry catalog that could change your routing economics. A new mid-tier model that is cheaper than GPT-5 Mini for your specific task profile could drop your per-request cost by another 10 to 20%. Test it in the sandbox before promoting it to production. Ninth, check the cost class compliance of any agent deployed in the last 7 days. New agents should not graduate from sandbox to production without platform review, but sometimes teams rush. Verify that every new production agent has the correct tags, the correct model assignment, and the correct credit cap. If an agent is missing any of these, flag it and require remediation before the next billing cycle. 10th, share the weekly summary. Post a 3-bullet update to your internal team channel. Total spend this week versus last week, any anomalies found and their status, and any upcoming changes like model tests or cache reconfigurations. This transparency keeps every stakeholder aligned without requiring a meeting. This checklist is not optional. It is the operational heartbeat of your cost architecture. Skip it for 2 weeks and small problems become big problems. Skip it for a month and you are back to guessing. The organizations that sustain their cost savings are the ones that treat this 15-minute ritual with the same discipline as their security patching cycle or their backup verification. It is maintenance. And maintenance is what separates professional architecture from experimental hobby projects. The architecture at a glance. If you take nothing else from this episode, take the 4 levers. Catching repeats with semantic caching, shrinking prompts with LLM Lingua compression, matching tasks to models with Azure AI Foundry routing, And buying capacity correctly with PAYG for variable workloads and PTU only for steady, high-volume production. Deploy these 4 levers behind a governance model that classifies every agent before it is built, audits every deployment after it is live, and enforces budgets automatically through Azure API management and Copilot Studio caps. That is the complete framework. It is not theoretical, and it is running in production environments today, and it can be running in yours within 90 days. Cost architecture beats cost accounting every time. The 4 levers, the 3 cost classes, and the 90-day roadmap are your structural defense against runaway spend. Build the framework, run the audit, and deploy the levers before your next billing cycle. Start this week because November is coming. And every experiment you built for free is about to start charging.